you very much for that, and good morning, everyone, or afternoon if you are in a completely different part of the world to me. As you can see from the screen at the moment, my name is Cliff Curtis. I am a former teacher. I taught for 38 years, from 1973 to 2011 in UK secondary schools, up to and including A-level, and also offered extra tuition for those students who were seeking to gain into Oxford and Cambridge universities. I've also been, or was, an examiner from 1984 right through to the end of 2017. So I had 34 years examining experience. And for the last 8 years of those, from 2010 to the end of 2017, I was actually the principal examiner for the Pearson Edexcel International GCSE specification. The last papers I wrote that were taken by delegates were in 2019. I'm also an author of chemistry textbooks. I'm the co-author of the Pearson Edexcel student books that support the teaching of this particular specification. Well, that's probably enough about me. So let's get on to this presentation. It would appear that it doesn't want to go forward on my screen, and I'm not sure exactly why. There we go. Okay, so welcome to this professional development training. It's designed for teachers who are looking to teach the Pearson Edexcel GCSE chemistry specifications. And the aim for today's session is to try to understand how the qualification is actually devised, to review the content of the qualification, to understand the assessment of the qualification, to explore how to plan the course and/or lessons, to understand the question types for the qualification, to understand the assessment objectives for the qualification, to practice using the mark schemes using student exemplar work, and to identify the support that's actually available from Pearson's. So the agenda, first of all, we'll look at how the qualification is devised, then look at the content, then look at the assessment, how we go about actually assessing your students, then some suggestions about how to perhaps plan the course, looking at the question types that your students are going to be faced with when they sit their exams, look at the assessment objectives and the command words associated with the questions that are set, and then have a close look at assessment objective 2, then assessment objective 3, and then have a look at the support that's available that's been supplied to help you by Pearson's. Okay, so first of all, just a little introduction, the welcome to Pearson. Okay, we are the world's leading learning company, and as the UK's largest award organisation, we're best placed to provide qualifications aligned to the British education system. Our international heritage stretches back over 150 years, and today we partner with schools and universities and employers worldwide, offering world-class, globally recognised qualifications to over 3.5 million students. So we're in a very good position to be able to offer qualifications for our international market that meets the criteria of the UK qualifications. So how is this particular qualification devised? There are two separate qualifications available. One is the International AS, IAS. The other is the International A-level, IAL. Both the IAS and the IAL are modular qualifications. There are 3 units at IAS, a further 3 units at IA2. The qualification consists of 3 externally assessed units, 1, 2, and 3. This can be awarded as a separate IS qualification or can contribute 50% towards the IAL qualification. With the IAL, this qualification has 6 externally assessed units. It consists of the 3 IAS units, units 1, 2, and 3, plus 3 IA2 units, units 4, 5, and 6. Students wishing to achieve the IAL must therefore complete all 6 units. So let's have a look at the content of each particular unit. For the 3 units of IAS, you've got units 1, 2, and 3. Units 1 and 2 you could perhaps call theory units, whereas unit 3 is a practical experimental skills unit. And as you can see in unit 1, you've got formula equations and amount of substance, atomic structure, bonding, and introductory organic chemistry with alkenes. In unit 2, you've got energetics, intermolecular forces, redox chemistry of groups 1, 2, and 3, introduction to kinetics and equilibria, and then organic chemistry, alcohols, halogen alkanes, and spectra. And unit 3, the students are expected to develop experimental skills and a knowledge and understanding of experimental techniques by carrying out a range of practical experiments and investigations while they study units 1 and 2. This unit will assess students' knowledge and understanding of experimental procedures and techniques that were developed in units 1 and 2. Very similar for units 4, 5, and 6, which need to be taken to complete the IAL. You'll see some of the topics cropping up again. For example, in Unit 4, kinetics crops up again. This will be a more highly mathematical approach to kinetics than would be in the IAS. The energetics crops up once again, and this time entropy is also included. Again, there will be a more highly mathematical aspect to it. The same with chemical equilibria. There will be a more highly mathematical component to the chemical equilibria. This is where you will start to talk about equilibrium constants, Kp and Kc. Again, with acid-base equilibria, there is a mathematical aspect to it again, calculation of pHs, calculation of Ka, and pKa, etc. And then there's some more organic chemistry that would build on what the students covered in units 1 and 2. In unit 5, you've got redox equilibria. Again, there is a mathematical aspect of this in terms of calculating E0 cells, etc. And now we move into transition elements and their chemistry, some more organic chemistry. This is where we move into the arene section. And then you've got organic nitrogen compounds, your amines, amides, amino acids, and proteins. And then to round up the whole of the organic section, you've got organic synthesis, where the students will be expected to be able to use all of the organic chemistry that they have learnt so far and apply it to a synthetic pathway. And the interesting thing about students, about Unit 6, is that it's very similar to Unit 3. The students are expected to carry out investigations, all of the experimental work from Units 4 and 5, but they do need a knowledge of some of the aspects of Units 1 and 2, for example, tests for anions, cations, gases, and organic functional groups. Okay, right. The assessment of the qualification. How do we go about assessing this particular qualification? Well, there's the IAS. Don't try and take in all this information because it's all in the specification. But the IAS, Unit 1, is a paper that carries 80 marks. It's a 1 hour, 30-minute paper. And it's available in January, June, and October. The paper has two sections, section A, multiple choice, and section B, a mixture of short, open response and calculation questions. We'll look in much more detail later on in the presentation about the type of questions that your students will meet. But the important thing here is they will be expected to apply their knowledge and understanding of experimental methods in familiar and unfamiliar contexts, as in the theory unit. Similarly, in Unit 2, you've got energetics, group chemistry and halogenoalkanes. Again, it's a 1 hour, 30-minute paper worth another 80 marks. Okay, and it's got 3 sections this time, not 2, because, and the difference is in section B, you've got extended writing questions, and I'll look at, explain to you what is meant by the extended writing questions and how they are marked, because they're marked totally different to all the other type of questions later on in the presentation. And in section C, you've got a contemporary context question. And Unit 3 is all about practical skills, and it's a 1 hour, 20-minute paper that's worth 50 marks. And the students are expected to develop their experimental skills and knowledge and understanding of experimental techniques by carrying out a range of practical experiments. And I'll talk a little bit more later on about the practical work that's involved and with some suggestions as to how to develop that. The same sort of thing at IAL, only the papers this time are slightly longer, 1 hour 45 minutes for Unit 4, 90 marks. Again, you've got multiple choice, mixture of short open response, calculations, extended writing, and in section C, you've got a data or calculation question. And in Unit 5, again, 1 hour 45 minutes long, 90 marks. You've got 3 sections, multiple choice, a mixture of short open response calculations and extended writing questions. And section C is a contemporary context question. And Unit 6, the practical skills, a 1 hour 20-minute paper worth 50 marks. Okay, all of that information is within the specification, so I would very strongly recommend you to look in detail at that to get a really good overview of the type of assessment your students are going to be faced when they sit their examination papers. Okay, so what about the unit results? There's no change to the uniform mark scale from the previous qualification. Units 1, 2, 4, and 5 have a maximum of 120 uniform marks. Units 3 and 6 have a maximum of 60 uniform marks. And the grades are awarded in Units 1, 2, 4, and 5 according to that particular scale. So in order to get a grade A in Units 1, 2, 4, or 5, they have to get 96 uniform marks. In order to get a grade A in Units 3 and 6, they have to get 48 uniform marks. IAS has a total of 300 uniform marks. IAL, a total of 600 uniform marks. And that's the cash-in code scores that are needed in order to be able to obtain grade A at IAS and grade A at A level. So 240 marks to get a grade A at IAS and 480 uniform marks to get a grade A at IAL. The A star, which is the top grade, of course, is awarded to students with 480 uniform marks or more, provided that 270 uniform marks or more are scored on the A2 units. So there's a qualification there with regard, they can't just score 480 uniform marks. They have to get 270 of those on the A2 units. Okay, one of the important aspects of the qualification is the specification content. Each topic and subtopic in the specification contains several specification statements. For example, that's topic 4. There's the introductory organic chemistry and alkanes, and you can see that there are 1, 2, 3, 4, 5, 6, 7, 8 separate specification points there, outlining what the students need to be able to do in order to be able to answer the examination questions that will be set on that particular topic. And the important thing is that every single question or part question is designed to access a specific statement from the specification. So, for example, which specification statement is the following qualification assessing? So if you happen to have a copy of the specification to hand, or you can click on your pack from, I think it's the bottom left-hand corner. I'm not sure exactly where it is on your screen, but you've got a pack. If you can bring that up on the screen, then have a look to see if you can find out which particular specification statement that question is actually designed to assess. And I'll give you a clue. It's in number 3. I'll give you a little while to have a look. No need to put your answers into the chat box. Just simply write down your answer on a piece of paper. The reason I say put down your answer is that you might want to use these with your students later, because I think it's quite useful for students to be aware of the types of questions that types of assessment objectives that each particular one is assessing. So the specification points. Okay, if you've managed to find it, it is actually 3.22. Be able to use the models in 3.20 and 3.21 to interpret the simple properties of metals, including electrical conductivity and high melting temperature. 3.20 deals with the structure and bonding of metals. Okay, there's another one. Which specification statement is the following question assessing? Which equilibrium shifts to the right-hand side when the pressure in the system decreases at constant temperature? This time it comes from number 9, section 9 in the specification. So if you've got that in front of you, have a look to see if you can actually find the exact specification statement. Okay, if you've managed to find it, it is actually 9.10. Be able to predict and justify the qualitative effects of changes of temperature, pressure, and concentration on the position of equilibrium in a homogeneous system. Okay, there's a couple of items just come into chat. I'll see if I can open the chat box, show chat previews. No, it's not opening the chat box for me. Ah, here we go. Oh, right, I'd say you're just putting your answers in. Yeah, okay, right. There's no need to put your answers in, but at least do keep a note of these. So you might want to use these with your students. It's entirely up to you to do so. Okay, there's something coming to chat. In October, variant for the practical science test in Unit 1. Do we need to cover them as well? I don't know what you mean by variant for the practicals. Um, but certainly I did mention earlier, movement of ions. Okay. Uh, well, I think if it was assessed in Unit 1, I think the answer is yes. Okay. Okay. Right. And the last one, which specification statement is the following question assessing? This is a question about the kinetics of gas phase equilibrium, and you're given a graph and you're asked to calculate the initial rate of the reaction, and you must show your working on the graph. Obviously, this comes from the rate kinetics section that will be in Unit 4. But the three marking points here are tangent drawn at t equals naught, calculation of gradient of tangent, and the calculation of the rate in moles per dm cubed per second. And I think that it is be 9.3, be able to calculate the rate of a reaction from the gradient of a suitable graph by drawing a tangent, either for initial rate or at time t. Okay, that was just designed to show you that there is a rhyme and reason behind every single question or part question that's set. They're all designed to assess a particular specification point. How are the specification points that are going to be assessed in any one given exam paper in any one given series? Well, that is decided by the chair of examiners, who keeps an overview of what assessments what particular specification points have been tested in previous papers, and therefore looking to assess some of the same ones in the next series, but different ones as well. And the idea is over the course of about 3 or maybe 4 series of exams, every single specification point will be covered. You'll appreciate that it's impossible to cover every single specification point in a single examination paper, because that would make it inordinately long. You probably have to have about a 3 or 4 hour paper to do that, and that's obviously not practical. Okay, right, let's move on to having a look then at planning the course. In order to plan the course, the key document is obviously the specification. And that document is available on the Pearson's. Sorry, but I have to have this phone in here. My wife will be answering it, so it won't cause us any concern. So the main document, obviously, it's available on the Pearson's qualification website under the International Advanced Levels section, and then you go to subsection chemistry, obviously. Okay, and it's listed under course materials. And you can see three separate things under course materials. You've got the specification and sample assessments, and that's where you'll find the specification. Okay, exam materials and teaching and learning materials, I'll mention these again a little bit later when I'm talking to you about the support that's available to you. So how do you make sure that you cover the content? Well, there are three key things. Obviously, the one I've already mentioned, the specification. And you must make sure that you cover all of the statements during the time available to teach the content, since questions can be set on any one of them. The next thing, of course, is the scheme of works, and these should contain what you teach in any given period and the order in which they will be taught. They're usually organised in batches of 1 or more weeks. The next slide will show an example. And the other thing, of course, that's important is lesson plans. And the lesson plan is a very detailed description of the course instruction for a lesson, and a daily lesson plan is developed to guide class learning. Details will obviously vary depending on the preference of the teacher and of the subject being covered, and of course the needs of the students. There actually may be requirements dictated by your school regarding how the plan is actually organised. And a lesson plan is your guide for running a particular lesson and includes the goal and what the student's supposed to learn. And I'll talk a little bit more detail in a moment about my thoughts about what could be included in a lesson plan. Okay, we have produced a scheme of work that again is available under the teaching and learning materials section in the Pearson qualification website, again under the International A-level exam site, obviously but in the chemistry section of that. And here is just an example of one page of this. The scheme of work covers absolutely everything in the specification. It goes all the way through every single topic. And this is just a possible week one. You might want to start on amount of substance. And as you can see, there's a lot of information there, including the aims and learning outcomes, which of course you can then translate into a lesson plan, and then example of classroom activities and teaching points and suggested resources. So you can have a look at those and see whether they suit your teaching style and your the learning style of your own individual students. And of course, you can take out any of those that you feel are useful and put them into your lesson plans, or add and put in the ones that you know that work for you and your students. You don't have to stick to this. This is just a suggestion. And again, it's available on the Pearson website, as I said. Okay. Right, so I did say a moment ago that I would give you some thoughts of what I think could be included within a lesson plan. And I do emphasize these are my thoughts. These are not Pearson recommended suggestions. They're just the way in which I used to go about creating lesson plans, and the one I developed with my department when I was head of chemistry. And I always liked to have a title to the lesson, followed by the time required to complete the lesson, followed by a list of any materials I needed. And these materials could be any worksheets that I was going to hand out to the students, or indeed, of course, it could be, if I was doing a practical, it would contain all the chemicals and equipment that I needed that I would then hand to my laboratory technician for him or her to get ready in advance in preparation for the lesson. A list of objectives, this is simply what I expect the students to know by the end of the lesson. So I've got a good idea of what I'm hoping that they will know. And I do say hoping they will know. Okay. Then, of course, there's a lead into the lesson that focuses on the students on the lesson skills or concepts. So give them an idea of what is about to come. Um, One of the things that sometimes is absolutely necessary, you all appreciate, I'm sure, if you've been teaching chemistry for any length of time, you will appreciate that chemistry is very much a sequential subject, and it builds on what has gone before. What you do at A level builds on what they do at GCSE, and what you teach in a couple of months' time into the course very often depends on what you have taught the month before. And therefore, sometimes it's quite useful to go through reviewing previous lessons when you know for certain that some of the skills and concepts and understandings that you taught them a month ago are going to be needed in order to be able to access what you're teaching on this particular lesson. It's very much an eye-opener for me to realize that students don't necessarily grasp the concepts that you've taught before. I always assumed early on in my teaching career that if I taught something, then that's it. They should know it, and therefore I don't need to go over it again before when I'm teaching another topic. And I found to my detriment that that was not the case. And therefore I very quickly learned that I needed to go over work very briefly at the beginning of a lesson when I knew that some of the concepts that I taught previously were going to be necessary for that lesson. Then there should be an instructional component. I believe there should be an instructional component. It's going to describe the sequence of events that make up the lesson. In other words, the order in which you're going to teach it. So including your instructional input and, where appropriate, guided practice by the students to consolidate new skills and ideas. And this guided practice could be in the form of questions that you ask during the course of the lesson. It could be in the form of perhaps a quick test that you might give them that can either be put up on the screen if you're using an overhead projector, for example, or projecting onto a screen from your laptop, or it could be handout in the form of worksheets, but some sort of guided practice to consolidate the new skills. I did not necessarily assume that those skills were being absorbed all the time during the course of the lesson. And I wanted to test that they got some particular skills, they got an understanding of it before I moved on to the next one. And then, of course, independent practice that allows the students to extend their skills and knowledge on their own. So this would be the homework task that you would give them, or you could give them independent practice if you've got time during the course of the lesson. So this could be done during the lesson, or it could be as a homework. And then, of course, towards the end, you've got some idea of how you're going to wrap up the lesson and discussion and answer any questions that they haven't yet asked during the course of the lesson. If you're doing a practical, then, of course, you need a risk assessment involved. And then, of course, for your own benefit, an analysis of how well the lesson has actually gone, give you an opportunity to reflect on it, and such as what's worked and what needs improving. So if you get their homework back and you find that the vast majority or the majority of the class are not answering some of the questions as well as you would have expected them to, and it's pretty obvious that they've not acquired the knowledge and understanding that you were hoping that they did, then you might reflect on whether or not it was the way in which you presented the information, and therefore might like to think, well, is there Do I need to go over this again? And the answer probably is yes. And should I go over it in exactly the same way, or could I approach it in a slightly different way in the hope that it might allow access to a larger number of the class? Okay, as I said, now that is just my own suggestions. They're not Pearson recommended suggestions of what should be in a lesson plan. And again, as I mentioned earlier, lesson plans, the format of lesson plans actually may be dictated to you by your school anyway, and you may have to follow those, but you may have the opportunity to incorporate some of those into it should you see fit. Just check, right, there's nothing else in chat at the moment, so we're okay there. Okay, moving on to practicals then. Very good opportunity for me here to emphasize exactly how important practical work is, particularly, of course, is if they're going to sit the IAL qualification at the end, they've got two 1 hour 20 papers in which they're going to be assessed on their experimental skills. And of course, it quite clearly states that some of the experimental skills will be tested in the theory papers as well. So the specification contains 16 core practicals. There are 8 at AS and 8 at A2. And I cannot stress strongly enough that the students complete these core practicals in order to develop the necessary skills that they will need in order to answer the questions in Units 3 and Unit 6. They don't have to do them individually. You can do them in pairs, or I would say the maximum a group of 3, depending on your access to the chemicals and the equipment. But as long as they do get some practice in doing the experiment themselves, the better. If it's absolutely impossible because you can't get the necessary chemicals or the necessary or enough of the necessary chemicals because of your budget, or you can't get enough of the necessary equipment again because of your budget, the next best thing is for them to see this as a demonstration. And if that is still impossible, then I remember in one country, and I taught many years, I did a face-to-face training session many, many years ago. It was almost impossible for them to get chemicals to do some of the practical work that was needed to do. Then I directed them towards the Royal Society of Chemistry website because there's a teacher section, teacher support section in the Royal Society of Chemistry website, which has got a lot of useful material, not only just for practical work, but for covering theory work as well. And you can access this by, you don't necessarily have to join the Royal Society of Chemistry, because you can join up as a teacher and access a lot of this material that's on there. So Royal Society of Chemistry website is a very, very useful website to get onto. The other thing is that there are a lot of other suggested practicals that appear in the specification. These are optional, but I would stress that the more practical work you do, the better, particularly practical work that helps increase the knowledge of those skills. The other thing perhaps I ought to mention is that it's not just a case of them knowing how to carry out each of these core practicals. They really should know why the individual, why each practical is carried out as it is. Perhaps it's best if I emphasize this with a particular example. Let's imagine the question said, describe how you would purify this sample of an organic compound by recrystallization. Outline the steps needed. Now that, of course, is sheer memory work. Hopefully they will have done a recrystallization, because that's one of the core practicals, part of one of the core practicals. So they should be able to list all the points. And when we ask that type of question, it's answered very well, with a lot of students getting very high marks. But if you then ask the question, why is the impure organic solvent dissolved in the minimum amount of hot solvent, then the number of students that actually manage to answer that question correctly drops significantly. And then when you go on to ask them why, when you cool the hot saturated solution, does the organic substance crystallize, even though they've covered this at GCSE and should know that the substance is less soluble in cold solvent than it is in hot solvent, again, the students appear not to know this. A lot of students appear not to know it. Start asking them, when are the insoluble impurities removed during this process? When are the soluble impurities removed during this process? Again. So it's a case of not only knowing the nitty-gritty of how the practical is actually carried out and being able to reproduce and regurgitate the method, but also understanding. And this obviously comes from quizzing them while they're doing the experiment, or quizzing them afterwards, and making sure that they have a full understanding of why the experiment is carried out in that particular way. Okay. You may add, of course, a substitute your own practicals too. Again, if you're going to do that, I would strongly recommend that you choose practicals that incorporate the skills that are being developed in the core practicals, so that you are increasing their understanding of those particular skills. Students will be assessed on practical skills in units 3 and 6, as I've already mentioned, and this will include testing the skills of students in both familiar and unfamiliar applications. So the familiar ones, of course, are the core practicals, or practicals that are very closely linked to the core practicals. Unfamiliar applications will be a practical, an experiment that the examiner, the question paper writer, is expecting them not to have any familiarization with, have done, or even seen, or even heard of, but will be linked to the skills and understanding that they've developed by doing the core practicals. They may be asked about planning, including risk management, and the selection of apparatus, and they may well be asked to give reasons for their selection of apparatus. Now, so why is it necessary to use a burette in this instance, and why, when you are adding, let me give an example, if you are doing an experiment in which you are trying to find out the rate of the reaction between magnesium and hydrochloric acid, and you're doing it in a conical flask, and you put in the magnesium and add an excess of hydrochloric acid, and you're following the rate of the reaction by monitoring how quickly the hydrogen is given off by collecting it in a gas syringe, then the student could well be asked, why is it not necessary to use a burette or a pipette to measure the 50 cubic centimeters of hydrochloric acid? Well, if it's in excess, it's not obviously necessary to measure it precisely. So you could use a beaker to measure the 50 cubic centimeters. It's things like that. They should be aware of where they do need to take precise measurements and where it's not necessary sometimes to take precise measurements. Other questions may cover data handling, including the use of significant figures and processing data and plotting graphs. Unit 3 is a written practical examination covering the skills and techniques developed during the practical work in units 1 and 2, which of course I've already mentioned. The unit content contains the 8 core practical activities, and the examination may include questions where students apply their knowledge to new practical situations, as I've already said. The students should develop their practical skills by completing a range of different practicals that require a variety of different techniques. Suggested practicals included at the end of each topic. So that's a bit of a recap of what I was mentioning on the previous slide. The points covered in Unit 3 also apply to Unit 6, except that students are expected to develop experimental skills and knowledge and understanding of the necessary techniques by carrying out a range of practicals while they study Units 4 and 5. But they also need to know the test for anions and cations and gases and organic functional groups from Units 1 and 2. So that's something that their students need to be aware of, that they could be asked on the paper for Unit 6 about the test for anions and cations and gases and organic functional groups, and that will have been covered at IAS, at AS level. Okay, so now we move on to the question types. The following question types will be set in Units 1, 2, 4, and 5, which of course I've already said are effectively the theory units. There will be multiple choice questions with 4 alternative answers labelled A, B, C, and D. There will be short response questions with a mark range from 1 to 5. There will be extended writing question worth 6 marks, but they're only in Units 2, 4, and 6, not in Unit 1. And of course, there will be calculations. And as I've already mentioned, questions in Units 3 and 6 will focus on practical skills. There is a typical multiple choice question. In order to answer the question, the students are asked to put a cross in the box next to the letter they wish to be considered for assessment. So in this particular question, they would hopefully put a cross in box C, because sodium chloride does not have a molecular structure. It's not a molecule. If, however, they did put a cross in A, and later on when they were going through their paper and checking it, they suddenly realised, hang on a moment, that's not the correct answer, then they put a line through that box as shown at the bottom there, and then put a cross in next to the letter they wish to be considered for marking. So hopefully then they change their mind and put the cross in C. If they suddenly realise that they've made a mistake and they do B and they decide, oh, I'll cross that out, and then think, oh, it's D, I'll put a cross there, and then they suddenly realise, no, that's wrong, and they cross that one out, or they put something in C and cross that out, and then they put it in D and cross that out, and they suddenly find, hang on a moment, I've got all 4 crossed out. What do? They simply write a letter in at the bottom there. What would happen is that when this particular question is scanned, the scanning process will detect that there are in fact crosses in all 4 boxes, and it will send it out for marking by hand so that it can be checked that way. Hopefully no student reaches that situation. There's a typical short response question. Explain why the coffee grounds might be considered to be a carbon neutral fuel, worth 2 marks. Note that there's a lot of lines left. There's always more than sufficient space left to answer the question. Students should not think that they have to fill up the space available. The time spent on each question should reflect the number of marks available. In general, 1 minute per mark. Though sometimes, of course, some questions are more complicated than others, and others are far less complicated. Some you can get answer the questions in 10 or 20 seconds per mark, and others you may have to spend a minute, more than a minute, sometimes 2 minutes per mark. But it all comes out even at the end of the day. That why have we left more than enough space? It's for students who make a mistake in the first two lines of answering their question, realize that they've done that. They should then cross out that work completely and replace it underneath with what they want to be considered as the answer. It's very, very important also to realize that the work that's been crossed out will not be looked at if there's a replacement answer. So if they write down in the first two lines the correct answer and then cross it out and rewrite something that's wrong, then what's been crossed out will not be looked at. Only the second answer they've written down, the added work. The other interesting thing is that if they cross out work and don't replace it with anything else, then what's crossed out will be looked at and will be considered for marking. So that's an important point. There's a typical extended writing question, and you can see it's worth 6 marks. Propan-1-ol is heated with concentrated solution of acidified potassium dichromate 6. Explain how the conditions affect the rate of the reaction and ensure that propanoic acid is the only organic product. Now, the way this is marked is by there being a number of what they call indicative points, and there are usually 6 of them. And those points will be listed in the mark scheme. Okay, and if they get all 6 indicative points, they get 4 marks. If they get 5 or 4 of them, they get 3 marks. If they get 3 or 2 of them, they get 2 marks. And if they can only get 1, they get 1 mark. And if they get none of them, obviously they score 0. In this particular instance, the 6 marks are those. Higher the concentration of the acid, the higher the rate. Collision frequency increases. Higher the temperature, the faster the rate. Because more particles have energy greater than the activation energy, and excess concentrated oxidizing agent ensures complete oxidation. There's one missing there, okay? I'm not quite sure what the other one was, but there should have been 6. But that's not the important point. The important point now is how are the other 2 marks allocated? Well, this table shows you how the other 2 marks are awarded. And it's awarded for the logical presentation of the information. So if the answer shows a coherent logical structure with linkages and fully sustained lines of reasoning are demonstrated throughout, they can score 2 marks. It's only usually that they'll get 2 marks if they've got 5 or 6 indicative points. It's unlikely to get 2 marks if they've only got 3 or 4 indicative points. They usually will only get 1 mark for reasoning. If they've got 0, 1, or 2, then they will get, they're likely to score 0 marks for reasoning. So that's how the other 2 points are given. And the question I get asked on a number of occasions is, can they answer this in bullet points? And the answer is yes, they can answer it in bullet points, providing, of course, they're showing their lines of reasoning and there are logical links between one bullet point and the next bullet points. So the bullet points follow a logical order. That's what I'm trying to say. Okay. There is a typical calculation. They were asked to write an equation for the decomposition of sodium azide, and then they were asked to use the equation they've written to calculate using the ideal gas equation, the mass of sodium azide required to fill a passenger airbag under standard conditions. So a typical calculation, and in this particular instance, because it was on a paper where PV equals nRT hadn't been covered, they were given the ideal gas equation and given R. It's because they're not allowed to use the data booklet. In this particular paper, it was Unit 1, so they were given the value of R on this occasion. Okay. Right. There's a little activity for you. Okay, so I'll leave you to have a look at that little activity. Again, you might like to use this with your students. So just jot down on a piece of paper. No need to put it into chat box because there are too many of you. Won't be able to see all your answers. Just answer that particular question, and then I'll go through what I think are the important points in a moment. Okay, so the first question says use crosses for phosphorus electrons, dots for the chlorine electrons, and circles for the oxygen electrons. That's the advice. It wouldn't be penalised at the end of the day if they use different symbols, but I would very strongly recommend you try to encourage your students to use the symbols that are asked for in the question. And then the second bit is explain the shape of the molecule using electron pair repulsion theory. So my thought process here is that first of all, they should show the bonding pairs, and then they should show all the non-bonding or lone pairs, if you want to call them that, on both the oxygen and the chlorine atoms, and that will give them the 2 marks. In C part 2, they need to actually state the shape of the molecule. They need to say that the region of bonding electrons repel one another, and then the 3rd mark to adopt positions of minimum repulsion. Okay, and notice how concise that you can be in your answer. Again, it's amazing how many students feel that they need to write a sort of mini essay to answer these questions. They don't. Just simple, concise, relevant points are all that's needed to answer these questions. So, what's the answer to the following question? Explain why iodine is very soluble in cyclohexane, but is only slightly soluble in water. Again, jot down your answers to that or keep them in your head for a decision as to what the important points are here. Okay, what's the important points in answering this particular question? Iodine soluble in cyclohexane, but only slightly soluble in water. Well, the thought processes that I would hope the students would go through when approaching this particular question would be thinking, if iodine is soluble in cyclohexane, then there should be a significant similarity in the type of intermolecular forces involved with both iodine and cyclohexane. I would hope they realise that iodine is molecular and that cyclohexane is molecular. So we're talking about intermolecular forces of attraction. They should be aware that iodine has only London forces available because it's a non-polar molecule. Cyclohexane is also non-polar, and therefore London forces. So I'd be hoping that they would be talking about the fact that cyclohexane and iodine form London forces between their molecules, so iodine is soluble in cyclohexane. In the case of water, the moment water comes into the feature, of course, we're talking about hydrogen bonding as one of the more significant forces of between water molecules because it's quite extensively hydrogen bonded, and those forces are quite strong compared to the London forces. So the London forces between iodine and water will be considerably weaker than the hydrogen bonds between the water molecules. And therefore, the iodine is going to find it very, very difficult to actually find itself attracted and break down and overcome the hydrogen bonding. So the next bit is hydrogen bonds between the water molecules are stronger than London forces between iodine and water molecules, so iodine is less soluble in the aqueous layer. So that's the sort of important points. Okay, so let's move on and have a look at another aspect of the examination papers as regards the exam paper writers, because they have to write their papers not only to the specification content and the specification points that the chair of examiners has actually told them to assess in any particular paper, but they also have to make allowance for the assessment objectives. And first of all, let's have a look at why we use them before we actually look at what they are. They're basically there to help make the exams fairer year on year. And the way in which they do that is that in every single paper of units 1, 2, 4, and 5, there has to be a certain percentage of marks allocated to each of the assessment objectives, and that has to be constant from one paper to the next. So that helps make the papers fairer year on year. So there will never be an overload of any one particular assessment objective being assessed in a paper. It will always be within certain parameters from one paper to the next. It also, of course, provides a structure for the question paper writers so that they can keep their questions within those parameters. It makes sure that the exams about skills are not just about knowledge, and I think we'll see how that is achieved in just a moment when we look at what the assessment objectives actually are. And lastly, of course, it can provide both you and your students with some reassurance about the types of questions that will be asked, because there will be some questions on each of the assessment objectives, and there will be a certain percentage of marks allocated to each of those assessment objectives. So what are these assessment objectives? Well, there's assessment objective 1, 2A, 2B, and 3. And A01 is to demonstrate knowledge and understanding of science. So all of those specification statements where it states students should know that, then that is straightforward recall. And the students are quite at liberty to recall word for word those knowledge statements in answer to a question. Basic understanding. There are a number of specification statements which say the students should have an understanding of. And when it's very straightforward understanding, that would fall into A01. A02 is where you take the application and knowledge of knowledge and understanding of the science that they've acquired from AO1 and apply it to both familiar and unfamiliar contexts. So it's where you apply the knowledge and understanding. AO2B is a slightly more difficult skill, a greater demand skill. It's similar to AO2A, but it involves analysis and evaluation of the information that you've been given to make judgments and reach conclusions. And AO3, which are only assessed in Units 3 and Unit 6, are all about experimental skills, including analysis and evaluation of data and methods. The types of questions that the students will be faced with will be in AO1, questions requiring students to recall and use the information that you've taught them, and also the basic understanding that they're required from the specification statements in the specification itself. AO2, questions requiring students to apply what you've taught them or to use the skills that they've developed as a result of their study. AO2B, questions requiring the students to analyse the information that's been given or the data that's been given and to make judgments and reach conclusions. And AO3, questions on practical work, associated practical skills such as planning, drawing graphs, analysing data and evaluating methods. So let's have a look at some typical questions from each of these assessment objectives. There's a typical AO1 question. It quite clearly states in the specification that the students should know what is meant by the term covalent bonding. So they should know that it is the electrostatic attraction between two nuclei and a shared pair of electrons. So that is AO1. It's a straightforward recall from the specification. Draw an electron density map for a molecule of oxygen. It quite clearly states in the specification that the students are expected to know the electron density map for a molecule of oxygen. Draw a diagram to show the shape of a water molecule and give the bond angle. Again, it's recall from the specification. It quite clearly states in the specification that the students should know the shape of the water molecule and they should know the bond angle in the water molecule. If it was the hydrogen sulfide molecule, that's a different matter. That would be AO2A because they're applying. AO2 question, what's the electronic configuration of the Sc3+ ion? There's no mention in the specification of the students having to know what that electron configuration is. But they are expected to know the electronic configuration of the scandium atom, and then they should be able to work out which electrons are removed from the atom to form the Sc3+ ion, and therefore they're applying their knowledge in order to reach an answer. So that is AO2A. Calculations. The vast majority of calculations will fall into AO2A, or sometimes they may fall into AO2B, but the majority will be AO2A. Some very, very simple calculations, like calculate the relative formula mass of a water molecule, is very simple and straightforward, and that probably will be classified as AO1, unless it's part of a very, very complicated multi-stage calculation. But even then, it may still be classified as AO1. So calculations tend to fall into AO2A. AO2B, here's a typical AO2B in a multiple choice question. And the reason why this is AO2B and not AO2A, there's no scale given for the relative abundance, and therefore they have to make judgments as to the value of those heights in order to get an estimate for the relative atomic mass of silicon. So that falls into the category of AO2B. They have to analyze the data that's presented to them and use that data to reach a conclusion. There's a typical AO3 question. Everything in there is all about AO3. Okay, a chemical test may be used to identify the hydroxyl group, identify a suitable reagent. The student suggested that oxidation of A would help to identify it. They set up that apparatus, identify the reagent mixture, etc. That's a question that was taken, I think, from a Unit 3 paper. And anyway, have a read of it yourself at a later stage. You've got a PDF version of the PowerPoint presentation, but I think you can see that that is a typical question that will appear in Unit 3 or Unit 6 type question papers. Okay. Right, well, activity 6, we've got an opportunity for you to use your newfound knowledge with regard to the assessment objectives 1, 2A, 2B, and 3 to start to sign in AOs. And again, I would strongly recommend that you make a note of the answers here because you may want to use these with your students. Because I think it's worthwhile that students appreciate which particular types of questions are being assessed with regard to the assessment objective. The major reason being, and I'll come back to this again later, is that I don't want them spending, and I hope you don't want them spending, large amounts of time answering AO1 questions when it's just simply recall of knowledge and basic understanding. Okay, there's your first one. Have a read of that question and decide which particular assessment objective you think that falls into. The question you've always got to ask yourself is, from the specification, does it state that the students are expected to know the colour of these changes? And the answer quite simply is yes, and therefore it is what's come up, AO1. Okay, that is AO1. Next one. Same question again, but part B. What is the concentration in moles per dm cubed of the potassium sulfate solution produced by this reaction in the endpoint, and give your answer to two significant figures? Remember what I said? Just have a look at the chat box. Oh, see, you're putting your answers in. There's no need to put your answers in. Don't worry about it. Okay, but just make a note of them. But what did I say about calculations? AO2A, of course. Okay, next one. Same question again, but part C, multiple choice question. You've got information about the uncertainties in each reading to measure the volume of the titration. Which statement is true? Really, obviously, it can't be AO1. It's from a theory paper, and therefore it is going to be an AO2. The question is it A or B? And you've got to ask yourself the question, are they analyzing the data that's supplied in order to reach a conclusion? The answer, of course, is yes, they are. So it's AO2B. Now, notice something rather interesting, that these are parts A, B, and C of the same question. And there are three different assessment objectives within the same question. And that's one thing that I think that perhaps both you and your students should appreciate and that is that a single question is not necessarily targeted at a single assessment objective. Okay, here's the next one. Baking powder is added to cake mixtures to make cake rise by releasing the gas during cooking. Baking powder contains an acidic derivative of tartaric acid and about 30% by mass of sodium hydrogen carbonate. Baking powder releases the gas in two types of reactions during cooking, one of which is neutralization. So, A1, give a name of the second type of reaction. So the question you ask yourself is, should the students know this from a knowledge of the specification itself? Which of course is yes, therefore it is A01. Part 2. Suggest why neutralization does not occur in an unopened container of baking powder. Obviously it can't be A01 because this is an application of their knowledge. And the question is, are they analyzing information and trying to reach a conclusion? If so, it is A02B. It, of course, is, certainly according to the examining team, was they were analysing information to reach a conclusion. So that does classify as A02B. Calculate the empirical formula. I've actually made a mistake here. That should not be A02B. I forgot to change the B when I did a paste and copy. That isn't A02B, that's A02A. Apologies. I copied A02B, pasted it in next to B1, and I should have changed the B into an A. Okay? So B1 is A02A, not what it says on the screen, A02B. And last but not least, write an equation for the neutralization of sodium carbonate by HK plus A2 minus. You've got to ask yourself the question, is this an equation that is straightforward and simple, in which case it's A01, or is it a very complicated equation, in which case it would be A02A? And this is a matter of subjectivity. The examining team, when they were assigning an assessment objective to this particular one, decided that this was a fairly straightforward and simple equation, and therefore should be classified as A01 and not A02A. If you wrote down A02A, I'm not surprised. Okay, and there's another one. And I think very quickly you'll realize, let's have a quick read through and decide. You've got 3, suggest why the flask in step 2 is frequently replaced, bromide step 3, blah, 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 explain the orange color around bottom flask. Sure, you've realized that that is A03. Right, there's a lot of information in the chat. Is it just that you've been putting in? Okay, that's all you've been doing, yeah. Okay, let's have a look at command words now. This is another aspect of the writing of examination questions. And I'm going to put questions in inverted commas because they're actually not really questions. We call them questions, but they're not. They're now commands. This resulted from extensive research that was carried out by the Pearson research team into uh, the best use of presentation, the best presentation of questions. Should they be asked as questions or should they be put down as commands? And there's the extensive research that they carried out showed quite conclusively that students tended to do better when they were commanded to do something rather than when they were asked to do something. So now all examination questions, apart from multiple choice, believe it or not, apart from multiple choice, have got to be in the form of a command. So what are the command questions? Well, every single question should have a command word apart from the multiple choice questions. It is an instruction to the candidates telling them what we want them to do. It is critical that the candidates know what each command word means so they can answer the question effectively. Analysis of students' answers over many years has shown that a lot of candidates do not fully understand what each command word means. Describe and explain are often confused with one another. Determine and deduce are often confused as well. All our qualifications in the International A-Level Sciences now uses a common taxonomy for command words, and these can be found in Appendix 7 at the back of the specification. Students can expect a range of command words across the demand range of the paper. There's just an example of a few of the command words that taken from Appendix 7. One of the things that I used to get my students to do was to download the 2 pages of this particular appendix and print them out and put them in the front of their folder. And every time they came across a question that had a specific command word, I said, go to those sheets, look at the command word, see what you are required to do as a result of that command word being used, and then try to answer the question doing what it says in the right-hand column. And over the course of the first year, by the time they come to sit their IAS modules, they had got a very good working relationship between a particular command word and what was required in order to answer the question from that command word. There is, of course, an increase in the demand of the various command words. According to Bloom's taxonomy, for those of you that are familiar with Bloom's taxonomy, state and describe, give, name, etc., all fall into the low demand section, whereas explain, suggest, compare fall into the middle of demand, and things like assess, analyze, evaluate, and discuss come into the high demand sections. So there is a cognitive demand linked to the particular command words. There's also some command words that are likely to crop up in association with questions targeting particular assessment objectives. So, for example, add, label, complete a table, describe, draw, explain, give, state, name, state what is meant by, or write a very familiar equation will crop into A01. That's the reason why that equation that we saw earlier in one of the questions the examining team fell into AO1 because it was a very familiar equation. AO2, calculate, comment on, deduce, evaluate, explain for more complicated ideas, or suggest, write an unfamiliar or more complicated equation would be AO2A. For AO2, you may well see comment on, deduce, evaluate, explain, again, suggest, but this time, of course, they would be analysing data that's supplied within the question to do that. AO3, any command word can be used in Units 3 and Unit 6. Okay, now what we're going to do now is to have a very, very closer look at AO2 questions, but you may be wondering why I'm not going to look at AO1. The reason is simple, because it's all about knowledge and basic understanding. And this is one that I feel that you as teachers really can't influence that much. The students either go away and learn what you teach them or they don't. But remember that students should still recognise AO1 questions and not spend time going beyond AO1. This is why I mentioned earlier that I think it's useful for students to have an awareness of which particular questions are targeting AO1, so they don't spend an excessive amount of time creating very complicated answers to them when it's only basic knowledge and basic understanding that's required. So what we're going to do for activity 7 is to use the mark scheme shown on screen to mark student responses on the next slides. And we'll go through each question one at a time. So once again, please there's no need to put your answers into the chat box, okay? Just simply make a note, because again, you may well want to use these with your students. You're quite at liberty to do so. I picked them to make specific points about things that students tend to do well and tend to do badly, particularly emphasizing common mistakes that students make. And if you can show them the sorts of common mistakes they make, hopefully they may not make them themselves. Right, now this question is about silver. Silver chloride decomposes in light, and the reaction was first used in photographic plates. All useful information, but doesn't help you answer the question, of course. Write an equation for this decomposition, okay, including state symbols. So what we expect them to write is that equation. We can a correctly balanced equation, and then to put down the state symbols. M2 is dependent on M1, or you can have M2 for correctly balanced equation if they have got a near miss. So AgCl2 or correct formulae but unbalanced equation. So, okay. Obviously, multiples and fractions are also accepted in the balancing of the equation. Okay, so there we are. Oh, I can lift that up. I didn't realize I can get that out of the way. Good. Right. I've put MP1, MP2 up there, and what I'm going to do after you've gone through and decided the number of marks should be allocated to each of those questions, I'm going to put ticking crosses next to MP1 and MP2, as I think fit. So go down through each of those. The first one's correctly balanced equation, but they've got a Q as the state sign for silver chloride, so they don't get MP2. Have a look at the second one. Incorrect formulae. There are two of them. But it does say that they can have correct balancing. But if you look at it closely, it's actually not correctly balanced because there is no CL2. So that tick is not correct. That should be a cross. Oh, sorry. The tick is for state signs, and they've got all the state signs correct. And they've got them correct on a near miss. So MP2 is correct. They get the MP2 mark. Excuse me, that was my mistake. Right, student 3. Very, very untidy presentation. You've got 2 AGCL and you've got what looks like a C, but if you look at the bottom, it's it could be the start of going into an S, though it's not quite the same as the S for AG, and it all depends on the level of generosity. If I was marking this, I would have been tempted to allow the state signs. So you've got correct balancing. Right, I think it's stopped again. You've got correct balancing and correct state signs. If you didn't give that mark for the AGCL state sign, then I would support you. If you did give it, I would support you as a team leader. Okay, and you were the examiner. We tend not to go against what an examiner does unless it is categorically wrong. The other thing you may be thinking is that with CL2, the 2 has been given as a superscript instead of a subscript, and we don't want to penalize that in the context of a chemical equation. So we allow that as a correct formula for balancing purposes. Right, student 4. First of all, is the correctly balanced equation? And the answer is yes. Have they got all the state signs right? The answer is no, because they've got AG for silver. Okay, so that's something that perhaps you could use with your students, and you could point out that although I think that that student meant to write S for AGCL in student 3, that it is very marginal as to whether that is an S or a C. Okay. Right, moving on. Here's the second question. Calculate the relative atomic mass of a sample of silicon using the isotopic abundant data supplied, and give your answer to 3 significant figures. So 1 mark for the expression and 1 mark for the evaluation. So what they need to do, of course, is to take the 28, the 29, the 30, and the 32 and multiply them by the relative abundance and then divide by 100. And that will give you 28.1586, which gives you 28.2 to 3 significant figures. Allow a transferred error on a minor slip as long as the final answer is somewhere between 28 and 32. Correct answer on its own scores 2, because that's off our regulations for UK examinations, which we apply in international examinations with Pearson's. Allow grams per mole, although atomic masses, technically speaking, do not have units. Only molar masses have units, but I think it would be very childish of us to penalise a unit of grams per mole. Okay, do not award any other units, of course. Okay, And so let's have a look. There's the first question. How many marks should be allocated to that particular one? Well, obviously MP1, okay, because they've done all that. But their final answer should be to three significant figures, which it is not. So they've only got 1 mark. There's the second one. At the moment you see 28.2, you know that it should be 2 marks, but they've given a unit, which is grams per mole, but it quite clearly says in the additional guidance, allow grams per mole. So 2 marks, because that unit is the only one that's allowed. But I picked that one out because if you want to use it with your students, it's quite useful to point out that relative atomic masses and relative formula masses do not have units. They are dimensionless, and therefore they shouldn't be putting the unit in. Only molar masses have units. Okay, there's the third one. Obviously, they've got MP1 because they've done all of the correct expression, but that is not a correct evaluation. So incorrect evaluation, only 1 mark. It should be 28.2, not 28.3. This is a classic example of where students have not appreciated significant figures. It's quite possible that they may have made a very slight incorrect input into their calculator and come up with an answer that gave 28.3 as the answer to 3 sig figs. Anyway, 1 mark only. Useful to point out that if they'd written 28.3 as their answer without any work in, they'd have scored 0. The fact that they've shown the work in allows them to score 1. Finally, a different way of presenting the expression, which is perfectly acceptable, 28.2, final answer correct, 2 marks. So again, another way you can show your students that they don't have to present the expression in a particular way. Okay, next question that falls into 2A category. Explain the trend in the first ionization energies of aluminium, silicon, and phosphorus. And the answer that the examiners were looking for is an explanation that makes reference to the following points: that the first ionization energy increases. Note the words in brackets are not necessary, so just the word increases is enough, or it increases, because the electrons are removed from the same subshell, second mark, and the number of protons has increased, and by 1 for each element is in brackets. So we would like to see by 1 for each element, but it's not essential. Now notice for second bullet point, you can accept electrons are removed from the 3p subshell, from 3p. You can accept allow they have the same shielding, but ignore same shell or same orbital. It has to be same subshell. Okay, and for bullet point 3, you can accept increased nuclear charge. Okay, so I'll leave you to do that one on your own, and then we'll go through the students 3, 4, and 2, 3, and 4 together. So try and work out that one on your own. Look for marking points 1, 2, and 3, which I'm going to list up as MP1, MP2, and MP3 as appropriate. So for marking point 1, you're looking for the word increases. Can you see it? Hopefully you've spotted it. Is there enough information to indicate that the electrons have been removed from the same subshell? I can't see enough information there to indicate the electrons are removed from the same subshell, personally. Is there any mention of the number of protons increasing or the nuclear charge increasing? No. A mention of number of protons, 1 mark only. Okay, second question. Look for increases. Doesn't take long to find it. Look for something that states because the electrons were removed from the same subshell. Or look for number of protons increasing. Doesn't take you long to spot the number of protons increasing. But I can't see anything that indicates number of electrons are being removed from the same subshell or being removed from 3p. I can't see anything about same shielding. So I don't think there's enough information there for MP2 personally. So 2 marks. Student 3. Doesn't take you long to spot energy increases. The first marking point. Second line, have a look at the second line. More protons, MP3. Is there any reference to number of electrons being removed from the same subshell or same shielding? Well, in fact, they've actually put down a better answer than the one that's in the additional guidance because, of course, the shielding can't be identical. Shielding remains constant as MP2. The reason the shielding can't be identical, of course, is because the outer electrons also shield one another within the same subshell. And therefore the shielding cannot be identical. The shielding from the inner electrons will be identical, but the overall shielding, of course, will not be the same. You keep forgetting that the electrons within shielding is a result of electrons repelling one another. I wish this term shielding was never ever invented personally, and we talk about electrons repelling one another. And the electrons within the same subshell repelling one another, of course, there are different numbers of electrons in the 3p subshell for each of those elements. So the shielding is not the same, but it is relatively constant. So this is a good candidate, very, very good candidate. Okay, so 3 marks. Next, student 4. On the very bottom line, they've got the order. So they get MP1. On line 1, 2, 3, 4, and 5, they've got, because the number of protons increases, MP3, but there's no MP2, so just 2 marks. Okay, and what we're going to do next is have a look at AO2B. But we have been going quite a long time. Can I suggest that we just have a very short break, just in case you want to go and get a snack or a drink of some description? Okay, my watch says 10:46. So let's say 4 minutes, and I start by my watch at 10:56. So look at your watch and add on 4 minutes, and we'll pick it up at that particular point, okay? Here's the first question. It's an AO2B question. Pure silver cups are too soft, so small amounts of copper added to make an alloy. Explain why the copper makes the silver less malleable. An explanation that says the layers of ions or atoms slide less well and over each other's in brackets, so it's not important here. But notice under the additional guidance, do not award the layers cannot slide over each other, or any words to that effect, of course. And then the second one is because the copper ions or atoms are smaller than the silver ions or atoms. Allow copper ions and silver ions have different sizes. Do not award just copper is smaller than silver. Ignore any comments about strength of metallic bonds or just copper ions disrupting the lattice. Okay, there's the first question, first student answer. So have a look for layers of ions or atoms slide over one another less well, and then any reference to the ions or the atoms being of different sizes. Well, we've got in the first part of the first sentence, as copper is add, the layer between the atom don't slip much easily. It's not particularly good English, but we don't penalise poor English, providing the overriding science is effectively correct. And I think that's good enough for the atoms or ions, the atoms slide less well. So quite happy to award MP1 there. Okay, this student then goes on to talk about difficult to break the intramolecular forces. We're not marking metallic bonding here, even though they've got the metallic bonding incorrect, so we can just ignore all of that lot and just keep on looking for some reference to different sizes. I can't see any mention of the relative sizes of the ions or the atoms, so MP2 isn't scored here. So I can only give 1 mark. I hope you agree. Okay, there's number 2. Different size of cations, MP2. Which makes them harder to slide over each other, MP1, because it does say from MP1, the ions slide less well over each other is acceptable. So cations sliding over one another harder, make it harder is MP1. So that gets 2 marks. Student 3. is an interesting one. The size of the copper is different than silver. Now, if we look at the additional guidance, it says quite clearly, do not award just copper is smaller than silver, or there's different sizes. But when you look at the next sentence, it says, so the copper iron atoms stay between the layers. So the question now is this student aware that there are actually ions present in the alloy, even though they've only mentioned one of the ions, copper iron? So would you like to err on the side of generosity and say the size of the copper is different from the silver alone would not be good enough for MP2, but then they've referred to the copper iron, which makes it clear enough that the candidate is writing about metallic particles and not just lumps of the two metals? And if you feel that this candidate is writing about the metallic particles and not just the lumps, then you can award MP2, which I am happy to do so. You may not be. If I was marking this as a homework, I probably would not have allowed it. But marking it as an answer to an examination question, I am tempted to be considerably more lenient. Anyway, let's move on. Copper iron atoms stay between the layers of silver to avoid the layers sliding past one another, of course, is effectively saying that the layers are now not going to be able to pass through one another. So that's equivalent to layers cannot slide over one another. So no MP1, so 1 mark only. So MP2 allowed for mention of copper iron in line 2. The line avoiding the layers slipping them over one another is a do not award, so only 1 mark. Okay, student 4. Well, different types of atoms I don't think is clear enough, because it could mean metallic, non-metallic isotopes, etc. So you're not going to get MP2 out of that, not as far as I'm concerned anyway. Layers cannot slide over one another is a do not award for MP1, so this candidate gets nothing, unfortunately. Okay, hope you are happy with that. Right, well, some questions for you to think about. This is not for you, for us to answer now, but just for you to think about. I'll put in my thought processes as well, but something for you to go away and think about with yourself, just on your own, or within your department with your colleagues. Is it better to present facts or teach principles, and why? Well, I think that's a pretty straightforward one, because AO2 is all about application of knowledge and understanding, and not just regurgitation of facts. So it's very, very important, in order to prepare your students to answer AO2 questions, you've got to teach a lot of understanding and principles. Okay, but what about questioning styles? Is it better to ask closed or open questions? Now, closed questions usually only require the student to answer yes or no, or those that only have one answer. What is the name of the catalyst in the Haber process? Iron. Okay, yeah, regurgitation. Open questions require the learners to think and formulate a response. How does the catalyst in the Haber process work? Open question. Obviously, my thoughts would be it's better to ask as many open questions as you can in order to get them thinking about how to formulate responses. Is it better to set formative or summative assessments, and why? Well, a summative assessment usually takes place after the pupils have completed units of work or modules at the end of a term or an exam. And the purpose of a summative assessment is to put students in rank order, just simply to award a grade, nothing more than that. And that could be to give a grade in a report at the end of a term or at the end of a year. Okay. A formative assessment, however, is where you put in the assessment with this sole purpose of finding out for yourself what the students do and do not know, and then providing feedback to them about what they have done well and what they have done not so well. So you were giving feedback and then supporting them in what they could do in order to improve on their performance if a similar question were to crop up again in the future. Again, I think it's fairly obvious which particular type of assessment is the better one to help your students prepare for AO2 questions in exams. And lastly, what else could you do to prepare your students to answer? And one of the things, of course, you could do is to give them as many past paper questions that are targeted at AO2. Either full questions or part questions. Where can you get questions that are targeted at AO2? Well, in many cases, because of the work we've done today, you may well be able to decide for yourself from past papers which particular questions are targeting AO2A and AO2B. But you can also, using Exam Wizard, and if you're not familiar with Exam Wizard, I will be mentioning this later in the support material that I'm going to mention. In Exam Wizard, you can actually extract AO2 questions from the past papers. There is the facility within it to say, I want questions solely targeting AO2. So you could pick out questions and create a test paper for them, or a homework assignment for them on AO2 questions. The more practice you give them, the better. Okay. Now, the other thing I think is so important, and something that I didn't really appreciate when I first started teaching back in 1973, yes, it was as long ago as that, is the importance of questioning. So something for you to think about. Think about one of the topics that you teach, which often has AO2 questions in the exams. One that springs to mind straight away for me is chemical equilibrium. Often has AO2 questions. What sort of questions do you ask in class when you're teaching this particular topic? By the time I'd been teaching 20 plus years and having taught topics on many, many occasions, I had a bank of questions. I didn't need to write them down. They're in my head. And I used to ask the same questions time and time and time again, trying to elicit understanding from the students and testing their knowledge to find out whether they fully appreciate what it is that I'm trying to pass over to them. If you haven't got that bank of knowledge because you haven't been teaching 20 plus years, then it might be a good idea to try and formulate questions. If necessary, have a chat with your colleagues to see if they've got any really good questions that they ask during this topic and incorporate them into your scheme of work. And if they're actually written down in your in your lesson plan, then you may well remember to ask those particular questions. Okay, but you must make sure that questions are helping your students to prepare for the AO2 type questions. So they've got to be open questions of some description. So really do think about it. Okay, and the other thing is homework. Now, back in 1973, when I first started teaching, I was told this is what you must teach each particular year, given a piece of paper, and said, and here's the homework timetable for every class that you're teaching. Make sure you set the one homework every single week. And I thought, oh, okay, right, I've got to set a homework. So I gave them homework. I didn't usually give much thought as to what I should put in that particular homework. So why do you set homework? Is it because you're told you have to, like I was told I have to, and therefore I did? The more experienced I became in teaching, the more I realised that my homework should in fact be very relevant to the lessons that I've been teaching and support it and perhaps extend their knowledge. So what sort of questions or problems do you set? In the early days, probably not particularly useful questions and problems that I set. But as I got more and more experienced, then I tended to set more and more suitable, useful questions that would develop their skills and understanding. What do you expect the students to gain from the questions that you set? So have a clear thought process about why you're setting a particular question. Will what they gain help them to answer AO2 questions? Right, so something for you to think about as you go away. Okay, for those of you that have been teaching quite some period of time, we have a saying in the UK, why are you bothering teaching your grandmother how to suck eggs? Which effectively means, why are you telling me something I already know? So I apologise to those who have been teaching for a long period of time and have been given lots of thoughts to everything I've been mentioning over the last 2 slides. But if you are a relatively new teacher, then perhaps some of the ideas that I'm putting forward here might set you thinking. I certainly hope so. Okay, now the other thing we need to look at, of course, is AO3, because they've got 2 papers, Unit 3 and Unit 6, to sit, and those questions will be targeted AO3. And let's remind ourselves of what it is. It assesses practical skills and understanding gained by students as they undertake practical work. And AO3 questions may require recall of practical techniques and understanding or application of these to new situations. It may also involve the use of experimental data and the evaluation of experimental methods or results. Here's a recall of a practical technique, a question that was set on a recall. Describe how the student should use the apparatus to determine the melting temperature range of a sample of their crystallized methyl-3 nitrobenzoate. So straightforward recall of a practical technique. There's a question on analysis of results. So they've been given some analysis of qualitative tests. Add in dilute sulfuric acid, you get a white precipitate, 2 possible cations, R, and then a sample of A was heated in a tube, a glowing splint was held in the mouth of the tube, a brown gas was evolved, and the splint relit, the anion is. So analysis of results, and the bottom one was there were 2 gases evolved in A was heated, a brown gas and a gas which relit the glowing splint. Identified the gases by giving their formulae. So analysing the results. Okay, typical question. There's analysis of results from data. Complete the table by estimating the volume of sodium thiosulfate that would be required for the titration time t, plot a graph, calculate the gradient, and include the units in your answer. Assume the volume of sodium thiosulfate required is proportional to the amount of iodine in the reaction mixture. Deduce the order of reaction with respect to iodine and justify your answer. Okay, so analysis of experimental results. Here's a question on evaluation of methods. Describe how to carry out recrystallization in step 2. Student 1 described how to carry out the recrystallization. And then there are 4 steps. The student's description of step A omitted important details. State how the method for step A should be changed and justify your answer. So this is an appreciation of why not only a knowledge of how it was carried out, but why it was carried out. When you ask the question, how to carry out a recrystallization and ask them to put down the various steps, then students do very well because they've memorized it. When you start asking them, why was the impure solid dissolved in the minimum amount of hot solvent, then fewer candidates get the answer. Why ask them at what stage were the insoluble impurities removed and at what stage were the soluble impurities removed, you get less answers than you do when you ask them to regurgitate the method. So here they have to have an appreciation of why each particular step is carried out, and when students, when incorrect information is given, then they need to evaluate this and justify. So that's an example of evaluation of methods. Here's the examiner's report on this. I thought because evaluation often is carried out so poorly, I thought I'd show you the examiner's report for this particular one. Many candidates have a good knowledge of recrystallization and obviously carried this out as they knew the reason for the errors in the description of student one. Others would benefit from more experience with this practical technique. Many candidates knew that the minimum amount of hot methanol should be used, but not all of them knew that this was to make a saturated solution. The use of hot filtration to remove the insoluble impurities was known by many candidates. The method described by the student to dry the crystals is seen frequently by candidates when they're describing recrystallization. It was interesting to see that some candidates understood why this would not work. Can I try to encourage you as much as possible to read the examiner's reports, because you will find in there evidence of good practice and not so good practice, which you can then perhaps put into your teaching to emphasize good practice and not so good practice when you're dealing with a particular topic. Not only in the units 3 and unit 6, but right the way throughout all the theory work that you do as well. Here's an example of use of data. You're given some relative electrode potentials and you're asked to choose from the standard electrode potentials to calculate E0 cell for the formation of manganate 6 ions in 6 solution and use the value of calculated value of E0 cell to explain why the manganate 6 ions cannot be prepared under acidic conditions. And then part 2, explain in terms of standard electrode potentials why manganate 6 ions can be prepared in a concentrated alkaline solution. So use of data. Here's the examiner's report on this one, which is quite interesting. The majority of candidates could select the correct 2 half equations needed to calculate E0 cell and realize that the reaction does not occur because it is negative. Those candidates who calculated a positive value should have checked their working, as they were told that the reaction does not take place. There were some very good explanations about the effect of using concentrated alkali. However, many candidates wrote vague answers and did not make it clear which of the 3 half equations they were writing about. Some candidates showed the working for E0 cell to be negative for the formation of manganate 6 ions under standard alkaline conditions, but they then wrote a positive sign so the reaction could be feasible, so they were fixing their results. And obviously can't be given credit for that. Okay, there's another aspect of teaching AO3, which of course is the terminology that's involved, and there's various, I've picked out 7 of them here, like anomaly, accuracy, precision, validity, reliability, uncertainty, and error. They're just a few. And when I come to deal with the support material available to you, I will mention the student's practical guide, in which you can get some further information about the meanings of each of these. But I will point out here that some of these are often confused. For example, accuracy and precision are often confused, and I will mention these 2 on the next slide. And also the others that are confused are error and uncertainty. Indeed, many years ago in examination papers, certainly in previous qualifications, the word error has been used in error. Please excuse the pun, when it should have been uncertainty. But now we have in fact got this right. As I mentioned earlier, I was co-author of the two student books that cover this qualification, and I've written the section dealing with error, uncertainty, etc., and trying to make it very clear what the difference is between these. But let's deal with accuracy and precision first of all. An accurate measurement is one which is close to the true or accepted value. And the accepted value comes from the work of many scientists who have measured that value, agreed with it, and published the value. You can refer to a textbook, data tables, or the internet to find these values. However, do be very critical of internet sources. They must always be checked for authenticity and bias. Okay. So what may happen in an examination question is you may be given, let's say, for example, some data to calculate the enthalpy change of combustion and get a value for it, and then be told that the true value or the accurate value is actually different, and then be asked why, in the light of how the experiment was carried out, and there will be a description of that experiment, this value is not in agreement with the accurate value. If repeated measurements give the same result each time, the measurements are said to be precise. So that's the difference between accuracy and precision. There is, of course, a different aspect of precision, and that is the precision of measurement. So, for example, mercury thermometers are only precise to intervals of 0.05 to 0. Plus or minus 0.05 of a degree C, because the 0 to 110 thermometers have intervals of 1 degree C. A digital thermometer, however, would be much more precise. It can be measured to the nearest 0.1 degree C. So there is precision of measurement as well, of measuring instruments. So there's another asset to precision. Error versus uncertainty. Error is the difference between the measured value and the true or accepted value of the thing being measured. Uncertainty is the quantification of the doubt about the measurement result, and this is often what was referred to as error in past paper questions many years ago, and that was incorrect. It should have been uncertainty. For example, a 50 cubic centimetre burette has an uncertainty of 0.05 for each measurement made, because the divisions are 0.1. Okay, a 25 cubic centimetre pipette has an uncertainty of plus or minus 0.06 cubic centimetres. The 50 cubic centimetre pipette, to my memory, is plus or minus 0.1 cubic centimetres. I think I'm correct if my memory is not failing me. There's a lot more information on this on page 16 of the teacher practical guide on the Pearson website, which we will come to in a moment. Right, I'm just going to have a look to see actually if there's nothing in the chat. That's good. Okay. Right, so now let's have a look at some questions on activity 3. Okay, let's see if I can get rid of that. It's annoying. Got it. Right. So activity 9, AO3 questions in exams. Okay. Here we are. We've got an experiment carried out to determine the enthalpy change of neutralization of sodium hydroxide and sulfuric acid. Okay. And we have to give a reason why the polystyrene cup in step 1 was placed in a beaker. And it's simply to prevent it from falling over, to stabilize it. Simply stabilize the polystyrene cup. Okay. Allowed to prevent spillages. Okay. So ignore any references to heat loss. So nice simple one to start us off. There we are, 4 students. Run down through those and see if you can find any references in any of them to some form of stability. Right, hopefully you've had a chance to look at all of them. In student 1, the mark scheme states to ignore references to heat loss, and so the start of this response does not negate the correct second part, okay, which says to avoid any spilling or loss of liquid, which is an allow in the additional guidance, so 1 mark. Student 2, insulation, just ignore that. To provide support is, to my mind, equivalent to preventing the polystyrene cup from falling over. So 1 mark. I think that's close enough to allow. The next one, to prevent heat losses or to insulate, ignore. So no marks, no mention of stability. And since the polystyrene cup is the subject of the question, this brief response to provide stability is equivalent to preventing the cup from falling over. So 1 mark. Okay, hope you're happy with those. The next one, state the purpose of measuring the temperature every 30 seconds for 2.5 minutes in step 2. And this, of course, is to determine a consistent or steady constant temperature before adding the sodium hydroxide. So let's look at the additional guidance, allow to determine a mean initial temperature, allow reference to achieve room temperature, ignore just to have a more accurate experiment, do not award references to temperature cooling, since this implies the effect after the reaction. Do not award is always a negate mark. So if they make reference to that, it can take away anything good that they've actually written. Whereas ignore means just ignore. So you don't penalise. A do not award is a penalty. Okay, so let's have a look at the questions. Student 1, it's done to obtain a more accurate temperature, okay, which is an ignore, by taking a mean of all of these temperatures. To achieve a mean initial temperature is an allow under additional guidance, so 1 mark. Student 2, to measure the initial temperature. That's not sufficient. It's not telling us about determining a constant, a steady or constant temperature. So just to measure the initial temperature is not enough. It had to be the mean initial temperature. So that's nothing. To get reliable readings, that's not sufficient. So no marks. To ensure the temperature of H2SO4 stays constant, yeah, that's good enough to get a consistent or constant temperature. So that's 1 mark. So again, you might want to use these with your students. Please feel free to do so and get them to mark them. And then you can tell them the correct marks afterwards. Okay, the next one, explain why the temperature was not measured at 3 minutes. And this is because, of course, the temperature will be changing because it takes time to add the 50 cubic centimeters of the sodium hydroxide. So for this one, there's a hell of a lot of allows in the additional guidance. For the first bullet point, allow the temperature was not uniform or the same throughout the mixture. Allow the temperature is still rising. Ignore just the temperature will be inaccurate. And for bullet point 2, allow because that's when the sodium hydroxide was added. So just allow when the sodium hydroxide was added. Allow because you cannot add the alkali and measure the temperature at the same time. Okay, is a practical point. Ignore references to the reaction just starting or hasn't finished. And last, there's a rescue mark down at the bottom. It's what we call a rescue mark. If no other mark has been awarded, allow 1 mark for the thermometer was used for stirring or the reaction mixture was being stirred. Okay? Right, so here we go. Student 1. The thermometer was used for stirring. Yeah, well, that would be allowed for 1 mark if there's nothing else. But let's have a look, see if there is something else. The reaction had not yet occurred. Okay. Temperature recorded would be inconsistent. We've got the temperature will be changing. So we've got MP1. All right. Now, since that's been awarded, we can't also award the thermometer was used for stirring because it's only a rescue mark if no other mark's been awarded. So you only get the MP1 mark there. Okay. So the reference to using the thermometer for stirring is only awarded if a mark for no other mark is given. So 1 mark in total. Right, student 2. At 3 minutes, the temperature is rising greatly. Yep, that's MP1. Okay, as it takes time for the temperature to be fixed. Okay, the reference to the reaction ongoing is actually in the ignore in the mark scheme. So they only score 1 mark here. Okay, hope you're happy with that. Student 3. Because it would take time for the reaction to take place, doesn't score. Temperature is measured before and after 30 seconds. Having the resistant, efficient enthalpy, no, just not worth any credit, as the acid is not stirred. The reaction needs to be completely mixed the solution without, yet the statement about the reagents needing to be mixed is a mark scheme allow for 1 mark. So, yeah, then, okay, so they can get that, just 1 mark there. Right, student 4, the reaction is reaching its optimum. The temperature change is too fast. Yeah, that scores MP1. The first sentence doesn't score anything. Okay, I can't see any evidence of MP2 there. Can't see anything about it takes time for to add the 50 cubic centimeters of sodium hydroxide or anything like that. So 1 mark only. Okay, right, well, moving on about teaching AO3 and doing practical work. As I've already mentioned, the specification contains a number of practical activities that form part of the subject content. Exam questions expect the students to be familiar with the methods for these practicals. Questions also expect the students to apply their knowledge of practical methodology to unfamiliar scenarios. Okay, so why should the students do practical work? Well, basically, so that they can fulfill everything that was on the previous slide. Okay, so what you've got to be asking yourself is, are the students getting the knowledge or skills from the practical activities that you're actually giving them? So yes, if they do the core practicals, but are you following that up with testing them about why the experiment's being carried out and not just leaving them to carry out the experiment and memorizing the method? Are you actually pushing them forward to appreciate the reasons why the experiment is performed in that particular way? And indeed, if there are any limitations to the particular experiment and any ways in which the method could be improved to get more valid results. When do you do practical activities? Before or after teaching a theory of a topic? There may be occasions in which it might be useful to do some practical activities to introduce the theory. This is particularly the case, perhaps in rates of reaction. It might be useful, for example, to do some simple experiments, getting them to appreciate that changing concentrations produces faster reactions before you go through the theory of why. Actually get them to hands-on practice of doing, getting the results for themselves and then explaining the results afterwards. Okay, right. Well, there is a whole series of support that we have available for you at every single stage. And the first one, of course, is the landing page in the Pearson qualification website for international A-level qualifications. And here, of course, you will find that course materials box over there, which has got, of course, the specification and sample assessments. It's got the exam materials, which has got all the exam papers, mark schemes, and examiners' reports. And it's got teaching and learning materials. And we'll have a look on the next side at what is in each of them separately, okay? And in the past papers, you have got question papers, you've got mark schemes, and you've got also, not mentioned there, examiners' reports. You'll notice that in the one that's up on the screen at the moment, it has in fact got padlocks next to them. The padlocked questions and mark schemes and examiners' reports can only be accessed if you've got a username and a password. And the username and the password is centre specific and can be obtained from your exams officer. The exams officer may be prepared to give you the username and password. If he or she is not, then they will simply download those question papers, mark schemes, and exams reports for you until they, and then you can access them that way. The reason they're padlocked, of course, is to stop students getting at them. Once the whole year has passed by, then they will be unpadlocked and you and students can access them freely. One good reason for padlocking them is, of course, it means you can use them for mock exams and the students shouldn't have seen it. Okay, teaching and learning materials. There's a whole load of information in teaching and learning materials, okay? There's exemplar materials, there are various guides, and I'm going to mention some of the guides in a moment. And there's past training material, okay, all sorts of things. And in past training content, there are some of the online training material there that you can access to see if you want to use that. And we're continually adding to this bank of materials, okay? Here's the exemplar material that's listed in that specification exemplar material section. Okay, only available for AS at the moment. It's been produced to support you delivering this international chemistry specification. It contains questions from the sample assessment materials and it shows real students' responses to these questions and indicates how the examining team will follow the mark schemes to demonstrate how students would be awarded the mark in these questions. We've selected some responses to 5 questions with mark schemes. So in other words, it's doing the same sort of thing as I've been doing with you today. Student responses, showing you and going through how it's marked. And here are some more examples, which again, you can use again with your students. But at the moment, it's only available for AS. Okay. There's a getting starting guide. One of the things about getting started with your AS course is that it's easy to assume one of two things: either that your students have retained all the essential information that they've been taught at GCSE, and have brought that with them into their AS lessons. Or you can think, well, I'm thinking they probably have lost most of that material. I'm going to spend some time at the beginning of the course going through the essential material. If you do that, you can suddenly find later on, you suddenly find yourself running out of time and rushing essential teaching towards the end of the course. The Getting Starting Guide is to try to avoid you falling into either of those two particular traps, because I doubt very much if they have retained all the essential information they need to start their AS course, and they will have retained some, and it's best not to spend excessive amounts of time at the beginning of the course going through that material. The Getting Starting Guide can help you overcome that. So I strongly recommend that you download that Getting Starting Guide and have a read through it and see how you could use it to support your students in the transition from getting into the course. Okay. The teacher support, mathematics support, covers the topics that students find difficult. These are mole calculations, enthalpy changes, reaction rates, equilibrium calculations, acid-base equilibria, and electropotentials. So again, I strongly recommend you download that. It also approaches the skills in the same way that the maths department does, so that you're not teaching maths in a different way to the way they're taught maths in their maths lessons. At least 20% of the marks on the examination papers will assess mathematical skills within the context of the relevant chemistry. So it's important that the students have got good mathematical skills in order to be able to access marks from those questions in the exam paper. The teacher practical guide support you and your students through all the elements of practical work in the international AS and A-level specifications. Okay, it explains how the requirements of the practical skills can be developed throughout the course using both core practicals and other specification content. So again, I very strongly recommend you to download that and read that through at your leisure. You'll gain a lot of valuable information about how to develop practical skills and support your students in giving them the necessary understanding and to answer the questions in Unit 3 and Unit 6. Oh, this is the transition guide. So this is the one that's very, very important with regard to transitioning your students from GCSE to A-level. And that's what I was talking about earlier, not the Getting Starting Guide. That's a completely different guide. My mistake. This is the one where you can use it to get your students transitioning from GCSE to A-level. For you, it's got a mapping of the international GCSE to the new international chemistry specification. It's got baseline assessments that you can give your students. Okay, it's got some summary sheets for them. It's got student worksheets that they can do. It's got practice questions they can do. The teacher version also has got all of the answers to these for the assessments, the worksheets, and the exam practice questions. If you know for certain that one of your students is going to do AS chemistry when they move into A-level courses, and you've taught them at GCSE and you know they're going to do A-level chemistry, then you might want to give them this or tell them to download this transition guide and direct them to doing various tasks within it during the holiday period between the end of GCSE and the beginning of A-level. Whether they do it or not doesn't matter, but that will be up to them. But at least you've given them some guidance. Okay. Scheme of work, as I mentioned, there is a scheme of work. It includes recommended teaching time for the topics, though of course this is adaptable according to the individual teaching needs. It's got a lot of classroom activities, teaching points, and suggested teaching resources. Okay, so again, I strongly recommend that you download that. It's got the objectives for students at the end of the topic and examples of integrated transferable skills, if you're interested in transferable skills, that is. So again, Download that. You don't have to follow that scheme of work. You can do if you want to, or you can adapt it to suit your needs and your students' needs. You know your students better than we do, and therefore, obviously, you need to produce schemes of work that are suitable for their learning styles. There are two topic guides. This one is written by a gentleman called George Facer, who has written a huge amount of supporting material for Pearson Edexcel over the years. George, unfortunately, is no longer with us. He passed away a few years ago and is sadly missed by all of us at Pearson's because he was a guiding light in terms of chemistry. And in fact, when I was first team leader for A-level chemistry, he was my chair of examiners. And the amount of chemistry I learnt from him stood me in great stead in my own classroom teaching. I'm very grateful to George. He wrote this guide to help with this particular specification, and included in it are some ideas on how to address common misconceptions in both the new and the previously included content from the previously specification qualification, possible teaching sequences for key specification points where there is new or challenging content, and it's got some worked examples that teacher could use to support the students in developing their understanding. The other guide is written by a lecturer at Southampton University, David, whose surname suddenly I have forgotten, but someone I do know very well, despite having forgotten his surname. It covers exactly the same sorts of things. The worked examples were added by me, actually. They're my addition into this. But there were some new instrumental techniques in this specification that were not in the previous one, and that's why we felt it would be useful to have a topic guide on instrumental analysis. For example, carbon 13 is in this specification and wasn't in the previous one. Okay, and there are links to external website that you can use. Now, there are other things that you can use as well, and that is Results Plus. Results Plus again can be accessed by you, providing your school is prepared to give you access to it by the relevant username and password. And if they do, what you can do is you can obtain a detailed analysis of your students' performance. You can identify potential topics, skills, and types of questions where students may need to develop their learning further. Now, this is particularly useful in the modular situation, of course, because if you've got students who have not performed that well in a particular module and they want to resit it, you can go back over that module and look at how your students answered the questions in that module, identify where their weaknesses were, and then work on them in preparation for their next sitting of that particular module. Okay, you can actually see the scores that your students got for each exams question. You can see that by student, or you can see it by class, or you can see it by group, depending on how you've set this up. You have to create the groups prior to this, but it can be done. There is, I believe, an online guide to how to use this. So if you're particularly interested in making use of Results Plus, it's there for you. A very, very useful tool indeed. Okay. It also gives you the opportunity to understand how your students' performance compares with class and Pearson Edexcel national averages. And it will give you data that may support effective learning and teaching approaches. So if, for example, you see that a cohort of yours have not been answering a particular topic that well, it may give you ideas or the incentive to reevaluate your own methods of teaching that particular topic and wonder whether or not there might be some useful changes you could make for those particular group of students when you next teach this topic. The other thing I mentioned earlier, of course, is Exam Wizard. Now, Exam Wizard is a tool that you may well find useful in producing exercises and past papers for your students, which they can use for study or you can use for classroom tests. Exam Wizard uses questions from past papers, so the bank of potential questions increases with each series to produce bespoke questions or question papers depending on what teachers are selecting to test. So it will save you time by creating your own mock papers if you don't want to use the mock papers, the exact mock papers that are padlocked in the past papers section. But more useful, it enables you to provide tests for particular topics or for homework or for revision activities. It uses the Pearson back catalogue exam questions to practice and develop these skills with your students. And you can gain access to the past papers and test questions to create tailor-made questions, learners' plans which target individual weaknesses. So if you spot the weaknesses for your student in a particular topic, then you can select questions by topic. Okay. And it works in conjunction with results plus to help you create exam practice and resources for the whole cohorts and individual students. The other thing that it will do is it will enable you to be able to select questions according to specific assessment objectives. So you could collect a whole series of test papers testing AO1 on a particular topic or across topics or across a unit, for example. Or you could collect AO2 questions. You can either do that by topic or by complete unit if you wanted to, or obviously AO3 questions are Unit 3 and Unit 6. So they're obviously can be assessed individually anyway. The other thing that is incredibly useful is post results is the access to scripts. And access to scripts is an online service included as part of your qualification fees, and it allows you to view your candidates' marked scripts online or download them as a PDF. It's free and gives you instant access from results day onwards. So it cuts down here, see, on the speculative inquiries about results, as schools have the time and the information needed to make informed decisions. So if a student comes to you and says, I think I did much better on this module than my mark, then with their permission, you can download their paper for that particular module and have a look at the marking in conjunction with the mark scheme, mark it yourself, and then you can turn around and say to the student, well, look, I've got exactly the same mark when I marked it myself. So I don't think it's worthwhile you going in for a remark. It's then up to the student to decide whether or not to take your advice or not. And if they don't want to, then they can go for the remark. But of course, they may then not get an improved mark and may, of course, lose their money. But that is a decision that they can make, but at least you can give them an informed decision. The Access to Script service provides a rich source of information, enabling detailed analysis to inform teaching and learning and support students again. It gives you insights into the visibility that performance data alone cannot provide. So you can actually get a lot of information from seeing how your students' work was actually marked, which is one of the reasons why I wanted to go through marking students' work during the course of this particular presentation. Pearson is the only awarding body to provide access to your students' marked exam papers included as part of your qualification fees. Okay. There are paid-for resources, and there are 2 student books, and there's the cover of student book 1, on which you will see my name, Cliff Curtis, and Jason Murgatroyd, Jason and I were the co-authors of all of the theory work in the two books. I covered all of the the physical chemistry sections, plus some of the work on the experimental skill side. Jason did the organic and the inorganic. The with David Scott bit, David did all of the oh gosh, I keep forgetting what they're called. The It'll come to me in a moment, okay? When I look at the next slide, I think, okay? The online teacher resource packs are designed to accompany the student books and are available as online subscriptions. I think it's about 800 UK pounds per year. But it does provide a detailed and comprehensive teaching plans for every section of the book. It may not be annual. Practice assessments accompanying the mark schemes for every chapter following the exam format. It's got student answers to the exam practice questions, practical support for the core practicals, including student worksheets, exam style questions, and teacher and technician notes. Remember, I kept saying that it's important to push the students beyond just a knowledge of the method involved and having an understanding and appreciation of why the experiments carried out that way and thinking bigger. That's what David Scott did. He did all the thinking bigger exercises. Okay, so that's why it just says with David Scott, because he wasn't an author of the theory work, the theory chapters. He just did the thinking bigger sections. Okay, so that's a paid for result that you can obtain. I'm not sure what the cost is, but you can easily find out from Pearson website. Okay, the other paid for results is a lab book that covers all of the core practicals, and that is the lab book. Okay, they've been written to support the Pearson Edexcel International A levels. They're globally recognized, which are globally recognized qualifications, of course. Yeah. The good thing about the lab book is that it gets all of their practicals into one particular place and not have the practicals and the sheets dotted about all over the place. Particularly important if some students are not that good in organising their files very well. You may find that it's actually cheaper to buy the lab book than it is to print off all of the experimental works as worksheets, or the experiments as worksheets, if you are charged for photocopying. If you're not charged for photocopying, it's another matter, but some schools charge for photocopying and some don't. So it may well be worthwhile buying the lab book. That's a decision that you make because you know your students best and whether they will benefit from having all of their practical work kept in one particular folder. As long as they then use that lab book in conjunction with their theory notes when they come for revision. Because remember, in units 1, 2, 4, and 5, there will be questions associated with experiments. They're not necessarily testing experimental skills, but there will be questions on them. So they need to be aware of that. Okay, the other thing is that we have got subject partner and advisor support. You have got Jonathan Wong, whose photo is at the top, and Tim Lawrence, whose photo is at the bottom, and they can be accessed through teachingscience@pearson.com, or if you're prepared to make a phone call using that number, okay? If you have any questions at all about this particular qualification of any description, including I don't understand why this wasn't included on the mark scheme, or I don't understand why this was included on the mark scheme, I don't, or you want any questions about the administration of the qualification, or anything at all, you've got any doubts, any concerns, any worries, then contact teachinsides@pearson.com, and one of those two people will get back to you with an answer to your query. You can also sign up to receive regular updates, and that sign up login is available to you on the Pearson website. Okay. The other thing is that there's Pearson Professional Development Academy. It's a high quality professional development is key to delivering impact learning. I'm sure you all appreciate that. To help you successfully implement international GCSE and international A-level qualifications in your school, we offer a range of training from introductory sessions to in-depth customized learning experiences. Okay, so you've got things like getting ready to teach, which is what I've been doing today. You've got understanding assessment and improving delivery, which I will be delivering in, I'm just looking at my timetable, in January next year, the 13th and the 15th of January. The International GCSE Understanding Assessment and Improving Delivery will be on the 13th of January, and the International A-Level will be on the 15th. And then you've got Enhancing Teaching Through Exam Insights. Again, I'll be doing two online events in February, the 3rd and the 5th of February for GCSE and A-Level respectively. And Marking with Accuracy and Insight, again, me. So you're going to get an overkill of me. Those will be in March, the 24th and the 26th of March. I'll be doing the Marking with Accuracy and Insight. Okay. I haven't even written the training packs for those yet, but they're on my agenda for post-Christmas. Once I've got Christmas over with, I'll be writing the training packs for the Enhancing Teaching Through Exam Insights and the Marking with Accuracy Insight. Okay, so please feel free to sign up for those if you think they may prove useful to you. Okay, and you can sign up and reserve your spot through that particular URL. Okay, you can also sign up to our newsletters and join the community to stay ahead of the curve. Okay, so you've got the PDF version of this, which should have that QR code on it, so you can simply scan it and fill out the form. Okay. Right, well, that brings me to the end of my presentation. Are there any more questions? Okay, if so, put them into the chat box, please. Oh, that's very nice of you. Thank you. Okay, if there are no more questions, then quite simply, I can move on and say thank you very much for attending today's session. I hope it's proved informative for you, and I've given you some ideas to go away and think about. Please don't feel that I've been lecturing to you. I see my role simply as providing some suggestions that may or may not prove useful to your particular teacher and students. Okay. Oh, thank you very much. Wonderful, informative session, sharing your knowledge. It's my pleasure. This is the one thing that is a passion for me and always has been for the last, what now is approaching 50 years of my life. Chemistry is a passion to me, and I just enjoy sharing the knowledge that I've gained from being able to work with very, very experienced and knowledgeable teachers and examiners. It's been a great pleasure for me, and I'm glad I could pass on something that's useful for you. Okay, well, that brings the session to an end. So we can end the session now, please. Okay.